Why do grain boundaries matter in creep? Have you ever wondered why some materials fail under stress while others hold strong? One key factor lies in the tiny structures called grain boundaries. Let's break down why these boundaries are so important when it comes to creep. Creep is the slow, time-dependent deformation of materials when they are under constant stress, especially at high temperatures. When materials are exposed to these conditions, grain boundaries play a vital role in how they behave. Grain boundaries are the interfaces between individual crystals, or grains, in a material. They are areas where the atomic arrangement is not as orderly as in the grains themselves. This disordered arrangement at grain boundaries allows atoms to move more easily. In fact, atoms can diffuse along these boundaries much faster than they can within the grains. This enhanced movement is a primary reason why grain boundaries are critical in creep deformation. During creep, grain boundaries serve several functions. They act as pathways for atoms to migrate, helping the material deform without breaking immediately. Grain boundaries can also slide past one another, which contributes to the overall strain in the material. This sliding is particularly significant at elevated temperatures, where creep is most likely to occur. Additionally, grain boundaries can be the starting points for voids or cracks because they are often weaker than the grain interiors. The size and characteristics of these boundaries can greatly influence the rate of creep. Smaller grains mean more grain boundary area, which can lead to increased creep deformation. On the other hand, larger grains have less boundary area and may slow down creep but could affect other mechanical properties. The type of grain boundary matters too. High-angle grain boundaries, which have a larger misorientation between adjacent grains, tend to be better pathways for diffusion and are more prone to sliding than low-angle boundaries. From a mechanical failure perspective, understanding grain boundaries is essential. Creep can lead to gradual deformation, causing components to lose their shape, develop cracks, or ultimately fail under sustained loads. For example, turbine blades and pressure vessels operating at high temperatures can suffer from creep damage that starts at these grain boundaries. In practical terms, controlling grain size and the characteristics of grain boundaries through material processing can improve resistance to creep. Engineers often design materials for high-temperature applications with specific grain structures to minimize diffusion and sliding. So, grain boundaries matter in creep because they are the features that allow atomic movement and deformation. Their presence, size, and nature directly affect how materials respond to long-term stress at high temperatures. Understanding these factors is key to preventing creep-related mechanical failures.